And certainly if you're writing homeworks, you can write them in Portuguese as well. You don't need to write anything in English. This is just a convenience for me that I do speak English here. So let me start today by tying some loose ends from last class and starting with something that was wrong. No one caught it here. But somehow I defined a simple Lie algebra I said that a Lie algebra G is called simple if there are no non-trivial proper ideals. But there's a pathological example that satisfies this, and we don't want to call that one simple. So, and let's add this. This was missing last time. And G is not one-dimensional. So the one-dimensional abelian Lie algebra doesn't have any non-trivial proper ideals, but it's not simple. Okay, so that was kind of going out there. All right, so what are we going to do today? So we'll talk a little bit more about this general stuff on structure. Then we'll talk a little bit about groups. Then we'll take a break, and then when we come back, we'll start proving Engel's theorem. All right, so what did I want to say from last time? Oh, yes, we ended up on trying to define central extension. So, again, definition. This is just to mention something we might learn later. A short exact sequence of Lie algebras is, well, G1 to G2, G3, 0. Let's call this guy I, this guy J. Morphisms of Lie algebras such that I is injective J is surjective, and the kernel of J is equal to the image of I. So we may have situations where we can have an abelian Lie algebra here, an abelian Lie algebra here, and not an abelian Lie algebra here. And this was the first non-trivial example that I wanted to give, was this one of the Heisenberg algebra. So before doing that, notice something. So just one way of producing extensions is, say you have G1 and G2 are Lie algebras. Then the vector space, which is the direct sum of G1 and G2, is also naturally a Lie algebra. Well, the bracket is what? So the bracket of a pair AB with a pair A prime B prime is just the pair AA prime. This is the bracket in G1, and BB prime, and this is the bracket in G2. So that satisfies all the axioms. And in particular, for example, I can just take the obvious extension of, so say now the question is, let's find extensions of K2, say, by K to 1. This is the one-dimensional abelian Lie algebra. This is a two-dimensional abelian Lie algebra. Why can I put here in the middle? Well, here I can put two things that I can think of now. One of them is just the sum K2 plus K1, which is a three-dimensional abelian Lie algebra, or I can put here the Heisenberg algebra. So the Heisenberg algebra, if you remember, how was this guy had three generators, P, Q, and H bar. Well, I can just have H bar here, and then just P, Q being commutative here. So I have a two-dimensional abelian Lie algebra. I can have P and Q being commutative here. P and Q do not commute here, but H bar, well, this is a one-dimensional Lie algebra, so this one is abelian. So that's an example of two different central extensions that have the same ends. And it's called this is called a central extension because the image of this guy is central inside of this guy. This H bar commutes with everything inside of the Heisenberg algebra. So different extensions of this form, they are characterized by some abstractions that there's a cohomological abstraction as to what are these possible extensions, and possibly, hopefully, by the end of the class, we'll be talking something a little bit about cohomologies of Lie algebras. Okay, so that's it, and now let's move on to, again, constructing examples of Lie algebras. So I said I didn't want to talk about Lie groups, and I don't want to talk about anything that is differentiable, but at least today, just one time, let me mention some algebraic versions of what Lie groups are. So usually, if you heard before, so Lie groups are manifolds. So here are my groups. And Lie algebras, well, I should say here, Lie algebras are tangent spaces to these guys. So in some way, Lie algebras are a way of linearizing these manifolds that are the groups. So there's a way of going from tangent spaces to manifolds, which is taking exponential maps. And this is what I want to avoid, because this exponential object is a transcendental object, something that is essentially non-algebraic. So let's do what we can do in algebra, which is the following. So let's start with a mock definition. I don't want to go into the theory of algebraic groups, but this would be enough for our purposes. An algebraic group should probably say linear algebraic group over F, so a field, is a collection. Let's write down finite. Of polynomials in the space of n by n matrices with coefficients in F, such that such that what? The following, let's define the set first. G of A is going to be the set of all matrices, let's put a name, let's say A, inside of n by n matrices with entries in A. I'll describe that, what is that in a second. Is invertible. such that A is invertible. And I want this set is a group. And here A is any commutative associative unital F algebra. Okay, let's walk this through a little bit. What does this definition tell us? So the idea is the following. I have just a bunch of polynomials. The coefficients of these polynomials are guys that depend on this field, F. Whenever you give me an algebra over this F, we can construct a group. So you should think of this as saying, well, the group GLN of n by n matrices with entries where? Well, you can just define it everywhere. So n by n invertible matrices with entries on any algebra makes sense. So that's the idea of this group, that you change this algebra, you get a different group of matrices with entries in a different algebra, but it's essentially the same, and it's given just by some collection of polynomials. For those of you who know algebraic geometry, it's just I'm saying that I have an algebraic variety defined over F. It's cut out by some polynomials P alpha. And it just so happened that this algebraic variety has an algebraic structure of a group. Well, and if you base change to any algebra, you get a group defined over that algebra. But now, let's give examples of what those guys are. For example, I can just choose the collection of P alphas of polynomials to be an empty collection. There's no polynomial. That's a good collection. So now you give me an algebra, A, and this set is the set of all matrices, n by n matrices with entries in the algebra A, which are invertible. Is this collection a group? Yes, it is a group. I can just compose them by multiplication, and each guy has an inverse. So that's a group, and that group is called GLN. So the associated group is GLN. It's called GLN of F. It's defined over F. Well, there's another group inside, which is the following. I can just take the determinant. That's a well-defined polynomial in matrices. But while looking at matrices that the determinant is 0, that's a bad idea. Oops. No one's stopping me. Of course I need this. I better have the polynomials vanishing on the matrices. Otherwise, that group is always the same group. The polynomial should play a role. Polynomials P alpha. And P alpha of A is equal to 0. So I can choose this collection now, P alpha to be only one polynomial and be just the determinant minus 1. So that's a well-defined one polynomial on the space of n by n matrices with entries in the field F. So now, whenever you give me an algebra, A, what is this group? It's the group of n by n invertible matrices with entries in A such that the determinant of A is equal to 1. Well, that's another group you should know. This is SLN. Defined over F. Let me define you another group over in a different way. Instead of giving you the set of polynomials, let me give you what that group is going to be for any algebra A. So for any algebra A, before that, let's fix B an n by n matrix with entries in F. So now for any F, for any A, let's define O of A, depending on B, to be the set of all A's inside of GL A. That's a group, which is this group when I use the algebra A, such that A transpose times B times A is equal to B. So I claim that this is a group. It's a subgroup of GLA. All right, so let's check that this is a subgroup at least of GLA. Say we have one matrix A and B are matrices of this group of A. That means that we have A transpose B A is equal to B transpose B B, and this is equal to B. And I would just want to check that the product AB is still in the group. So I want to check that this, but this is just B transpose A B A B. I'm just using that the transpose of the product is just B transpose times A transpose. Now this guy is B, and therefore this guy is B. Now, how do you check that this is a, the fact that it's a subspace, that's also kind of trivial here. All right, so it is a subgroup, and this guy is, if B is, first of all, if B is non-degenerate, symmetric, then this group is called the orthogonal group. But if B is skew symmetric and non-degenerate, this is called the symplectic group. But I haven't given you the polynomials defining this group. Actually, I urge you to try to find them. All right, so why am I wasting time in defining these groups? There's a neat way in algebra of understanding what vector fields are, what tangent spaces are, in an algebraic manner. Somehow, going from the manifold to the tangent space, I said it was a linearization process. It's sort of like taking Taylor expansion up to order 1 only. That's passing to the tangent space. But we can make sense of what Taylor expansion up to order 1 is by just choosing a particular algebra A over the field F. Suppose you have an algebraic group like that. I can choose my algebra A to be the algebra F, let's say polynomials in epsilon, mod out by the ideal generated by epsilon squared. So this is an algebra. This is an associative commutative algebra. It has one guy epsilon whose epsilon square is 0. The multiplication table here, this algebra as a vector space is just F plus epsilon F. This is as a vector space. And the multiplication table is just really trivial. It's just you write any guy like this. This is just AA prime plus epsilon BA prime plus AB prime. And the rest is epsilon square is 0. But now we have if we started with an algebraic group, in particular, we have G of A. And this guy will carry the information of the tangent space. So definition, Lie of G is going to be the following. It's going to be the set of X in GLF. This is a Lie algebra GLF, such that the identity matrix plus epsilon X is in G of this A. And this is a non-trivial construction. First of all, why this makes sense. This is the identity n by n matrix. G is an algebraic group like that. So in particular, this matrix here, this is, again, it's an n by n matrix because this is in GLn. So this sum is an n by n matrix whose entries are, well, elements of the field, like this is 1, plus epsilon elements of the field. So I can think of this as an n by n matrix which has entries in this algebra. So it looks like, well, now I can ask, are the polynomials defining the group on that matrix 0 or not? Is that matrix invertible or not? If that's the case, then I call this matrix here an element of Lie of G. So the theorem we want to prove is that this is a Lie algebra. So theorem, this is a Lie algebra. And actually this is a Lie subalgebra. Since certainly it is a subset of GLN. So it is a Lie subalgebra of GLN. It's not entirely trivial, actually. But anyhow, so let's prove some things. So again, let's grab an X. So let's start with the proof. But before saying so, though, we see that if we were on this G being a manifold, a Lie group, then I am expanding up to order 1 near the identity of the group. So this somehow should give you the idea that we are taking a tangent space, a tangent vectors to the identity of the manifold. So this set of matrices are really just tangent vectors, arrows starting from the identity of the group. This is purely algebraic way of saying that. Proof that this is a Lie algebra. So X is in Lie of G. By definition, if and only if this identity plus epsilon X is in G of A. A from now on is going to be the algebra of dual numbers. But then in this algebra, let's check that this guy is an inverse. So what is this multiplication? Well, the identity times the identity plus epsilon factor in common of what? This is the identity times X, so that's X, minus X times the identity, so that's X. And then the rest is epsilon squared, which is 0. So this is an inverse for this matrix. Let's look first at the bracket. Let's check that the space is closed under the bracket inside of GLN. That's somehow the easy part. All right. So let's say we have two guys. Let's say we have X and Y are inside of the Lie algebra of G. I want to check that the bracket is still in the Lie algebra of G. This is just again similar to saying I have two tangent vectors. I want to check that the Lie bracket is still a tangent vector. Well, so by definition, this guy is in G. This guy is in G, but G on different spaces. So this guy is in G of F epsilon divided by epsilon square. Its inverse is also there, because this is a group. This guy is in G of F epsilon prime divided by epsilon prime square. Its inverse is also there because this is a group for any algebra. And then I can just multiply by epsilon x I plus epsilon prime x. All right, let's carry this multiplication. This is just multiplications of two groups. Now, how can I multiply them? There are elements of groups on different spaces. I can just, this multiplication doesn't make sense a priori. But the point is that there's an algebra that contains these two. I can think of the algebra F epsilon epsilon prime divided by epsilon square, the ideal generated by epsilon square, and epsilon prime square. This is a well-defined associative commutative algebra. Therefore, G of this guy is a well-defined group. And certainly, all these guys make sense as a group in here. They're matrices whose entries are in these algebras, and they're invertible and everything. All right, so now I can multiply them. So let's multiply them. All right. I hate doing these multiplications. Let's see. So this is minus epsilon x. Oops. No one is telling me that this is a y. You were laughing. You knew this. You were laughing all the time. You knew this. You know this was a y. Why didn't you tell me? That was going to give me a nice 0. All right. So this is I minus epsilon prime y, I plus epsilon x, I plus epsilon prime y. Let's expand this thing. So certainly the first order is I. It's the multiplication of the identity everywhere. At order epsilon, what do we have? So we have minus epsilon x times y times y times y everywhere. But then I have a plus epsilon x times I everywhere. So that guy is going to be 0. At order epsilon prime, I have a minus epsilon prime y times the identity everywhere, but then a plus y times the identity everywhere. So that guy is also 0. The next order is epsilon epsilon prime, where I pick this xy times the identity, and then what else do we pick? And we're picking a minus yx that right? That's epsilon, epsilon prime. Sounds right. But therefore, and then the rest is always 0. Now, it contains an epsilon square or an epsilon prime square. But that's enough, because now we see that this guy is an element of the group. And because the product is a product inside of a group. But this is an element of a following group. It lives in an algebra that is smaller. I can consider this as a one variable divided by the ideal generated by this guy being the square is 0. So this, which is the bracket inside of GLN, is still in the Lie algebra. Okay, so now we have a so we have this space which is closed under bracket. What do I need to check that I have a Lie algebra, a sub-Lie algebra? What was the definition of a sub-Lie algebra? Am I missing something to check? Or is this enough already to check that I have a sub-Lie algebra of GLN? We just check that if I have two guys, x and y, in Lie of G, their bracket is still in Lie of G. Do I need to check anything else? Come on, just a wild guess. Someone has to. I have all the time in the world. I mean, 2 hours can pass really, really slowly. Just give me a guess. Or probably it's already done. So let's work on what were the definitions of a Lie algebra then. So if I have a Lie algebra and I want to check that I have some subset that is a subalgebra, what do I need to require in that subset? It's close on the bracket and I can be here forever. Someone must know the answer, or at least guess the answer. Guess wrong. Yeah, sure. For what? ¿Qué estoy haciendo mal? Probablemente estoy haciendo algo mal. ¿Queda mal? Plus x, y. Tem razão. X and y. Minus y. Minus yx. That's yx. That's correct. Huh. What am I doing wrong? That's right. X, y. I'll have to check this. One. Não, mas... Não, pode fazer a... Não, então pode fazer a multiplicação destes dois primeiro, los dos últimos no final, está tudo bom. De todas formas, a pergunta continua. ¿Qué falta? Nadie quiere ni siquiera arriesgar. No one's going to try to guess. Okay, so if I have an algebra, a requirement, the very first definition of what an algebra was, not even a Lie algebra, is that it has to be a vector space. So it's not clear at all that I have a matrix in GLN such that these conditions satisfy. And I have Y also that this condition is satisfied. Fine, their bracket seems to satisfy this condition again. But their sum is not clear that it's there. So we need to check that. We need to check that this condition is linear in this X. So that somehow is the condition that V in a tangent vector is a linear object. And that's non-trivial. So this is the definition, so let's not erase this. And here we'll need the fact that our algebraic group was defined by polynomials. So let's continue on this side of the board, because this is the point. X is in Lie of G, if and only if this guy is in G of A. That's true. This means that this guy has to be invertible, but there was a condition on the definition of G of A. G of A was the set of n by n invertible matrices with coefficients in the algebra A, and the polynomials defining the group in these matrices should be 0. So that's a condition of being in the group. Now, since I have a group, I do know that the polynomials on the identity should be in the group. So this I know is 0, because the identity should be part of the group. Now the good thing about this algebra of dual numbers is that I can Taylor expand linearly on these guys up to order 1, because epsilon squared is already 0. So if I do the Taylor expansion with respect to X, I'm going to have only two terms. Order 0 in epsilon or order 1 in epsilon. So let's do that. Well, we will take, what is the Taylor expansion of that equation? I have 0 is P alpha of I plus epsilon X. But this is, well, at order 0 in epsilon, P alpha of the identity, plus at order 1 in epsilon, the sum of all the derivatives of this P alpha with respect to the entries. I mean, these P alphas were polynomials in the entries of the matrix, of the n by n matrices. So let's call those guys I and j. We're summing over I and j, evaluated at the identity. Now these are numbers. Now they are not necessarily 0, but they're numbers. Times, well, epsilon, because it's our order 1, and xij. But the whole point here is that, well, this is 0, by what we said before. So this condition here is now a linear equation on these unknowns, on the entrances of my x. These are just numbers. So if I have one matrix X that satisfies that equation and another matrix Y that satisfies this equation, the sum is also going to satisfy this equation, because this is a linear equation in these entries. These are just numbers. So that proves that this is a subspace. So usually, actually this is a common mistake. I've seen it several times, that people check that you have somehow a subset, you check that the bracket is still inside of the bracket, and then you say, okay, this is a subalgebra. And there's papers with these kind of mistakes. All right. The point is now, whenever you have an algebraic group, you can produce now this Lie algebra associated to it, which is just taking the Taylor expansion of the algebraic group with values in these dual numbers algebras. So let's see what are the Lie algebras that we already know with respect to these groups. I mean, there's a reason why their names. So first of all, the Lie algebra of GLN is GLN. Well, there was no, the proof of this is obvious. There's no P alpha. The set that defines GLN, there's no P alpha. So the only thing I need to check is that for any matrix in little GLN, I can have an inverse. But this is the thing that we just checked here. So for any matrix in little GLN, the identity plus epsilon x is in big GLN because it has an inverse, which was essentially the only condition defined in this group. So this is tautological. The Lie algebra of SLN, remember, this guy is the group defined by the polynomial. There's only one polynomial, which is the determinant minus 1. This is SLN. Let's check this. So on the one hand, we have this algebra that consists on n by n matrices, let's say x, such that their trace is 0. And on the other hand, the definition of this side is that the identity plus epsilon times that matrix should have determinant 1. Let's write it down. So we have 1 plus epsilon x11, epsilon x21, epsilon xn1. And here we have epsilon x12, epsilon x1n. Here 1. And on the diagonals, we have the entries of the identity. So we have epsilon n22 up to 1 plus epsilon xnn. And outside, we have epsilon x2, 3, and so forth. So everything that is off the diagonal has an epsilon. Everything that is on the diagonal has a 1 plus epsilon something. That's kind of clear here. So now I need to compute the determinant. There's two things. One is that this guy has an inverse. We already checked. For any x, this has an inverse. The other thing to check is that, well, the polynomial vanished. So we need to check that the determinant of this guy is equal to 1. What gives us that condition? Well, the determinant consists of picking out of each row one entry, some shuffling, but the point here is that if I pick any guy outside of the diagonal, I'm going to have an epsilon squared. Well, unless I pick one in the diagonal, one outside the diagonal, but that's going to be a 1, so that's not going to contribute. So the only way that I can contribute to this determinant is to have all of the guys in the diagonal. But that's going to be 1, just this product of all these guys, plus the epsilon linear term. And the epsilon linear term is, well, at each point I need to choose x11 and then 1 on all of these other guys, x12, x22, and then 1 on all the other ones. So I get x11 plus x22 plus xnn. And then the rest is of order epsilon squared. So the determinant of this matrix is just 1 plus epsilon, the trace of the matrix. This is kind of a mock thing because somehow what you may have used in calculus is that there's a relation between the exponential of the trace and the determinant of a matrix. It's just that we are tricking things up in such a way that the exponential vanishes at the first step because we already have an epsilon that squared is 0. So essentially this is the exponential of the trace. It's just that epsilon squared is already 0. But anyhow, so the point is that this is the determinant, and if I want this guy to be 1, then better. So this is equal to 1 if and only if the trace is equal to 0. But this was the definition of being in little SLN. So we checked that the Lie algebra of the Lie group of determinant 1 matrices is the algebra of traceless matrices. All right, so let's check. Tricky because I didn't give you the polynomials for the orthogonal ones. But let's check that the Lie algebra of this group that I called OB, OBN, I think. Oh no, let's just say OB was, is little OB that we defined last time. So on this side, so the statement is, recall the definition here. This definition was that it consisted of matrices A transpose B plus BA is equal to 0. Those conditions. Those were n by n matrices satisfying that condition. And here, the condition on the group was that A transpose B A, well, let's not use the same letter, that for the elements of the group, was equal to B. That was the condition. Now, if I want to look at the Lie algebra, well, then I better take I plus epsilon X, take the transpose, B, and now this G better be I plus epsilon X, and this should be B. Well, up to order, the constant order, this is just B times the identity, so that's B. Plus, up to order epsilon, we have X transpose B times the identity, plus the identity times B times X. And I want this to be B, so we better have this guy being 0, which is the condition for the Lie algebra. All right, so that shows somehow that the Lie algebra that corresponds to having orthogonal transformations on some vector space is the Lie algebra that we were calling orthogonal. Okay, let me finish and take a break in a second, but let me just make a comment, because now, from now on, we're going to move on into just trying to prove an actual theorem about the structure theory of Lie algebras, but it's geometrically it's easy to see what the statement of what these groups are acting on vector spaces and what their defining properties are. This GLN is, well, the group of automorphism of a given n-dimensional vector space. Any automorphism is there in this group. So it makes sense that, well, just any endomorphism of the vector space is in its Lie algebra. This Lie algebra, this Lie group, is the group of guys that have determinant 1. That means that they preserve a volume form on that vector space. And the notion of preserving that volume form in the Lie algebra is interesting because it corresponds to having trace 0. This is something like having divergence 0 for vector fields. As for the orthogonal condition, well, being in the orthogonal group, say this B is non-degenerate and symmetric. Just take it to be the identity, that matrix. This group is the group that preserves lengths. So it's easy to see what the group acting on the vector space is. But however, this orthogonal Lie algebra satisfies this condition. That is, if you take the transpose, if this was the identity, it's just that the transpose is equal to minus itself. Where does this come from? And it comes just by differentiating, taking the linear approximation to those Lie groups. All right, so we'll take a break, we'll come back, and then we'll prove Engel's theorem today. Now I guess it's not going to be entirely trivial, but at least it's going to be entirely formal. We might cut it short though. Let's see. Somehow what we're aiming for is we had two sets of examples of Lie algebras. Some of them looked like GLN, SLN, SP, 2N, SO, well, SON, and some other looked like TN, DN, and NN. Remember, these were triangular matrices, diagonal matrices, and upper triangular matrices. Somehow what we're aiming is to say, well, let's divide all the examples of Lie algebras into two classes, some like this and some like this. That'll take a few classes, but let's start with a couple of examples. So, lemma. Let A be an operator, so an endomorphism of V, such that A is nilpotent. That means just that A to the n is equal to 0 for some n. For some n large enough. Let's suppose this V is finite dimension. Then add A. Remember, this is again an element of GL, is also nilpotent. This is a confusing statement. So I have a matrix that acts on a vector space, say by multiplication. So you can think of this A is just a whole matrix with some entries, and it acts on the vector space V, which are just row vectors. And if you just multiply this matrix n times, this guy is going to be 0 for every vector. And the statement is that, well, actually, if you just now take this matrix and commute it with another matrix now. Remember, this was taking the adjoint. Is take the bracket. And take the bracket again with the same matrix A. And take the bracket again several times, n times, well, probably more than n times. This is also going to be 0. So that's a statement of this lemma. Let's prove it. Actually, this is a very simple statement. What does it mean to take the adjoint? The adjoint is in a very precise place. It's in GL. So if you remember, the bracket is multiplications and then multiply them in different order. So the adjoint of A acting on B is, by definition, this is A times B minus B times A. Or which is the same thing as multiply on the left. So left multiplication by A acting on B minus right multiplication by A acting on B. So these are just the operators. These are endomorphisms of, well, GLV, which are LA of B is just AB, and this is RA of B is just BA. So far I'm saying trivialities. But the point is that these operations, LA and RA, are nilpotent operations. Well, indeed, because LA to the n is just the operation of multiplying on the left n times by a. So this is just the same thing as left multiplication by a to the n, which is the same thing as left multiplication by 0, which is just 0. The same thing for right multiplication to the n. This is just right multiplication by a to the n, and this is 0. So I have two nilpotent operators, and I want to claim that their sum or their difference is nilpotent. Well, if I am to take a power of this and say, well, I want this some power to be 0, well, that would be quite helpful if these two guys commute. If there were just two nilpotent matrices and then you take their sum, it's not true that the sum of two nilpotent matrices is going to be a nilpotent again. But these two guys commute. So that's the second part. Left multiplication by a and right multiplication by a commute. Actually, for any two matrices, that's true. And that's just the fact that GLV is associative. So you can just take any two different guys. Let's apply this to any C. To any C. On this side, what this is LA of C times B. I'm multiplying on the right by B. And here is RB of A times C. Oops. I did want to have a, sorry. Otherwise, I'm going to run into problems. That was going to be a problem. Let's do this here. So now this is just A times CA. And here is just A times CA. Let's put the B later. And now this is just by associativity, the same thing. So I have these two guys commuting. Therefore, now LA minus RA to the probably 2n, yes, to the 2n is equal to, well, if they commute, now I just can do this 2ni LA, well, there's going to be a sign to minus 1 to the I, perhaps. And then LA to the I, RA to the 2n minus I. But now, if I, and this sum is from I is equal to 0 to 2n. So if I is bigger than n, this guy is 0. And if I, well, bigger or equal than n. If I is less than n, then this guy is bigger than n, and this guy is 0. All right, so that shows that whenever you have an endomorphism that is nilpotent, then taking the adjoint by that endomorphism is also an nilpotent operation. The converse is certainly not true. I mean, and this is a big remark. There are matrices that are not nilpotent but their add, so matrices say A, but add A is nilpotent. A good example is the identity matrix. The identity matrix commutes with anything, so the adjoint is already 0. So in particular, it's nilpotent. But the matrix itself is not nilpotent. Any diagonal one is not nilpotent. But good examples of nilpotent matrices are upper triangular matrices. These we already know that are nilpotent. So their adjoints is also nilpotent. I said at some point that Tn, so upper triangular matrix, not even strictly upper triangular matrix. If you take the bracket of two of these guys, you get an upper triangular matrix. So somehow we're going to use this in a second. So now the statement that follows is to say that it's aiming and saying that whenever you have a Lie algebra that consists of nilpotent operators, it's going to be upper triangular matrices. So that's what we want to prove. So then we can try to start separating Lie algebras. If you have enough nilpotent operators, just take them out. Let's worry about nilpotent Lie algebras from one side. Let's worry about simple Lie algebras on the other side. All right, so, right. Theorem. I think this is angles theorem, or probably angles. What people call angle might be a corollary of this. Let G inside of GLV be a Lie subalgebra consisting of nilpotent operators. So they are nilpotent acting on V by multiplication. Then there exists, let's assume V is not 0 and is finite dimensional. Everything here is finite. Then there exists a non-zero vector in the vector space that is killed by all the operators at the same time, such that G on V is equal to 0. So this means AV is equal to 0 for every A in G. I mean, clearly, if I had upper triangular matrices, so that's a Lie algebra consisting all of them of nilpotent operators. In this basis, there is one vector that gets killed by all upper triangular matrices, this one. So the vector 1, 0, 0, 0 everywhere gets killed by all upper triangular matrices. But the problem is that a priori I could have a Lie algebra, a sub-Lie algebra of GL that has some matrices are upper triangular, which are certainly nilpotent, and some other matrices are lower triangular, which are certainly nilpotent. And now, how do I find one vector that gets killed by all of them? So we'll use this previous lemma. All right, so let's prove this theorem. So the proof is going to go by induction. By induction on the dimension of G. If the dimension of G is 1, this is almost obvious. I have only one operator on a vector space that is nilpotent, I want to prove that there's one vector that gets killed by that guy. Well, if an, say n plus 1, is equal to 0, but an is not 0 acting on V, an is not 0, that means that there exists something that a and v is not 0, but a times a and v is equal to 0. So this guy would do. So when the dimension is 1, we know. We have one vector that gets killed by all of G. So now let's assume that the dimension is bigger than 1. And let H inside of G be a subalgebra, a proper subalgebra. The idea is to try to find one vector that gets killed by all of H and try to extend this to the whole G. So we have some subalgebra of H of G. H acts on V, on the vector space V, by nilpotent operators. I have one vector because the dimension of this guy is less than the dimension of G. By the induction hypothesis, I can find one guy that gets killed by all of H. How do I add the extra operators coming from G that are not in H? So for this, we're going to use the previous lemma. Since H acts by nilpotent operators, the adjoint action of H, so let's see, add A is nilpotent for every A in H. That was the previous lemma. But the adjoint action of H, since G is an algebra, G is stable by this adjoint action. So H acts by nilpotent operators on G by the adjoint action. But H is a subalgebra of G. Therefore, H acts on itself. And H is a subspace that is stable by the adjoint action on G. So the adjoint representation defines a representation of H of the same subalgebra H on G mod H, on this vector space. Again, the fact that the bracket of something in H with G is still on G is the fact that G is an algebra. But the fact that H is stable is the fact that H is a subalgebra. All right, so now we have H acting by the adjoint representation, or by taking brackets on this space, and it acts by nilpotent operators. And this is by the previous lemma. Since H acted by nilpotent operators on the vector space V. All right, but now the dimension of H is less than the dimension of G, so I can find, by induction, we can find a vector, say B, inside of this vector space, let's put a bar on it, such that, well, the action of H on B is 0, such that A bracket B bar, or let's write it as an adjoint, such that the adjoint action of A on B bar is equal to 0 for every A in H. This is the induction hypothesis. I have a smaller dimensional algebra acting on a vector space by nilpotent operators. I can find one vector that gets killed by the whole algebra. What does it mean to be 0 in this space? Well, let's take a preimage in G. So choose any B. Now, this is in G, a preimage of that. Oops. So this condition here, that the adjoint action of A on B bar is 0 on the quotient space, is just that the adjoint action of A acting on B, well, belongs to H, which is the same for every A in H. Or the same thing, A, B belongs to H for every A in H. I didn't define you what the normalizer is, so I'm not going to mention it now. But let's put a star here so that I recall this later. All right, so here we can use a trick. We were free to use any subalgebra we wanted, and we got there. So the point is, we started with any subalgebra, H, and what we could find is an element outside of this algebra. B cannot be in H, because this vector was not 0. So the point here is that B is not in H. Otherwise, B bar would be 0 in the quotient. And we found, therefore, an element outside of the algebra such that, well, if you take the bracket of anything in H with this guy outside, it lands again in H. So in particular, H plus the field times B is a Lie algebra. It's a subalgebra of G. And H is an ideal inside of that subalgebra. And H is an ideal well, now we can do two things. Either I could have started here. Let H be a proper subalgebra of maximal dimension, or I could just replace H by H by plus FB and repeat. So feed this algebra, it's called this algebra H2, and put it back here. This is another proper subalgebra. Let's suppose it's a proper subalgebra. Just repeat, find another B2, such that this gives you a bigger algebra. At some point, you have to get to the whole algebra G. G was finite dimension. In other words, if I asked this algebra to be of maximal dimension, well, then we should have here, this is the whole G, because this is a bigger algebra. So what we ended up doing is we found a way of expressing our Lie algebra as a sum of two algebras. Well, we have an ideal of codimension 1, and this generated out of the complement. Okay, good. So now, oops, this was, well, hope you took note of this. All right. Yeah, I shouldn't have erased that. All right, so now, let's look at, we know, let's write this. We know there are vectors in V such that AV is equal to 0 for every A in H. There are some non-zero vectors just because of the induction hypothesis. If I have two such vectors, their sum is also such a vector. So the space of all such V's is a vector space. So let's call W is the space of V in V such that HV is equal to 0. This is a subspace of V. And it's non-empty. At least there's one. Moreover, W is G invariant. What does that mean? It means that if you give me any element, say A in G, and any V in W, then, and let's say X in H, I want to claim that A times V is again in W. But this is if and only if, well, being in W means that for any X, X times A times V has to be 0. But this is if and only if I take their bracket, X times A times V is the same thing as, well, let's write it as X times A minus A times X plus A times X on V. This is equal to 0. And this is equal to the bracket of X with A acting on V plus AXV. The bracket of X with A, since H is an ideal, is in H. So this is 0. And here I have X of V. X is in H. So this is also 0. So W is invariant by G. Well, now we're done. We wrote down G as a sum of an ideal plus a subspace of dimension 1 generated by one operator. This whole algebra acts by 0 on this space W. And this operator preserves this space W. So I have B acting on W. And it's nilpotent. It better have a non-trivial vector that vanishes. So B is nilpotent. Acting on W, because W is invariant by G. So there exists a non-trivial V in W such that V is equal to 0. And that certainly, so V does the trick. That proves the theorem. It's a non-trivial statement. But the point is, if we have a Lie algebra where every matrix in it, I mean, it has to be a Lie algebra inside of GLV. So it's a Lie algebra of matrices, and every matrix is nilpotent, then there's one vector that gets killed by the whole algebra. Actually, an observation, it's in those lecture notes. I remember when I took those notes. This surprised me. But it's trivial anyways. Observation. you can ask the following question. Say you have a subspace. Instead of algebra. Namely, if I give you a subspace inside of the space of matrices consisting of all matrices that are nilpotent, is it true that you have one vector that gets killed by all of them? And the answer is no. So we really need the algebraic structure, the Lie algebra structure for this space. All right, so now the standard applications are all obvious. Let's see. I'll just write a couple of them and then we can just finish. All right. Okay, the first thing to do is the following. Say G inside of GLV consists of nilpotent operators again, dimension is finite everywhere. Then there exists a basis for V such that G consists of upper triangular matrices. Proof, just induction. So the proof is just repeat the theorem inductively. So step one, there exists by the theorem, there exists one vector V which is non-zero inside of V. Let's call it V1, which is non-zero, and the whole of G kills it. In particular, G acts on, now not on V, but on V mod V1. Well, I should say F times V1. But now you have G acting again by nilpotent operators, so pick V2. V mod F V1 such that G kills it there. But that means that if you take a preimage of V2, oops. Then we have this equation here means G V2 lives inside of the span of V1. And so forth. That way you get a flag where you would have span of V1. This is where G of V2 lives. Well, but then G of V3 would live inside of the span of V2 plus V1 and so forth. And now choose the basis is the basis what you would get. V1 up to Vn where you finished, that's the trick. Okay, good. So now all algebras consisting of nilpotent operators are upper triangular matrices. You can write them as upper triangular matrices. Actually, I didn't need this G on GLV. I could have phrased this in terms of representations. So let's do that. So the statement is, if you have a finite dimensional representation, observation, if pi from G into some GLV is a finite dimensional representation, consisting of nilpotent operators, then there exists a basis such that pi of G is upper triangular or consistent upper triangular matrix. All right. So why we prove this kind of stuff? The idea is that from now on, we want to get rid of nilpotent algebras. I mean, upper triangular matrix, okay, fine. I mean, there's a lot to be said about the algebras of upper triangular matrices. Solvable Lie algebras are also quite an important subject. We'll talk about this in a second. But then we'll divide the class of at least complex Lie algebras in finite dimensional ones in two classes, this kind of algebras and the simple ones, and then we'll try to classify the simple ones. Now, let me define for any Lie algebra so that we finish defining what a nilpotent Lie algebra is. We can define a sequence or two sequences. The central sequence is as follows. We take, I never remember if it starts with a 1 or with a 0, but let's say that G0 is equal to G. And let's say G1 is equal to G. And let's say G2 is equal GG bracket with G, and so forth. So GK plus 1 is equal to the space GK bracket with G. So this is an inductive sequence. And let's define another one. Let's say G0 is equal to G. G1 is equal to G. G2 is equal to G1. And GK plus 1 is equal to GK. Okay, so the first observation is this sequence is of inclusions. Certainly, this guy is inside of the algebra, and this guy certainly is inside of here, and so forth. this guy is inside of GK. The same here. I mean, these are obviously proper inclusions. These are all ideals of G. These are all ideals. We can prove this in a second. We can prove this by induction. But moreover, GK, well, G0 is equal in this side, G1 is equal in this side, but now this guy here lives inside of this guy. But it may not be the same. Definition. A Lie algebra is called nilpotent and notice that I'm giving a definition of nilpotent that does not depend on having this representation in GLV. If GK is equal to 0 for some k. So if this sequence at some point stops, that Lie algebra is called nilpotent. Notice that if, say, GK plus, well, GK minus 1 is not 0, but GK is 0, right? Then what does that mean? This means that GK minus 1 G, this is by definition GK, this is 0. This means that this guy here has to be inside of a center. Because it commutes, any element here commutes with the whole algebra G. So a nilpotent Lie algebra has a non-trivial center. Because, well, GK minus 1 is non-zero. But then, I mean, we can go on. We can just take, this is an ideal, we can just grab G modulo the center. Or let's just take it modulo GK minus 1. And this guy is still going to be nilpotent. So we can play this trick and do the same thing of finding these bases that we did for upper triangular matrices. You start with a nilpotent Lie algebra, and well, take the last one. You find that it's central, mod it out, check that the quotient algebra you get is nilpotent, and try to understand that quotient. Is a lower dimensional Lie algebra, so it's easier to understand, and you can go further down. We'll probably do something about that next time, and not now. I want to finish before. Now, algebra such that this sequence stops are called solvable. So if gk is equal to 0 for some k, G is called solvable. Oops. Well, the typical example for nilpotent Lie algebras we already know, it's upper triangular matrices. And the typical example for solvable Lie algebra is non-strictly upper triangular matrices. So if I take non-strictly upper triangular matrices, is solvable, but not nilpotent, and strictly upper triangular matrices is nilpotent. Well, but then since this ideal is inside of this guy, certainly that means it's solvable. This, by the way, allows me to correct something because it wasn't in your exercises last time. I didn't want to do the two-dimensional example, but let's work it out now because that's an example of a solvable one. Last time we said, okay, let's look at the non-abelian two-dimensional Lie algebra. I think the exercise is to find a matrix form for it. Well, then this algebra G is generated by two guys. Let's say they're called A and B, linear independent objects. So what is G1? G1 has to be generated by, well, all possible brackets of this guy. A with A is 0, B with B is 0, so this can only be A with B. So this is a generator of G1. I don't know what happens with G2 yet. But now, that's a one-dimensional space. So there better be some guy C that is not in FAB. So let's take such C. There should be a non-zero guy here. Let's put a name to this guy. Let's call this guy D. And let's look at the bracket of C with D. This bracket can only be a multiple of D, of AB. Because, well, this was an ideal. G1 is an ideal. And it's a one-dimensional ideal, so whatever bracket I take on any guy in my Lie algebra, it has to land in this one-dimensional space. So this is a multiple of D. So let's say this is, say, alpha times D. But alpha is non-zero. If alpha was 0, the algebra was commutative. All right, but then let's replace this C by 1 over alpha times C, so that this is isomorphic to the two-dimensional algebra with two generators. We can call them C and D, and the bracket of these two guys is D. And now we can compute the whole series. So if we have G0 is just G, G1 is F D, G2 is I take the whole G and I take the bracket with G1, and it's the same thing, and it's the same thing, and this continues. This never stops. But we get, this is G, G1 is FD, G2 is, well now in order to compute G2 I need to take the bracket of D with itself. So this guy is certainly 0. So this is an example of a solvable algebra that is not nilpotent. So it can't be, for the exercise you can't be looking at upper triangular matrices. Okay, so I don't remember if I asked you in the exercise to compute, but looking at Victor's notes I see, and these are kids at MIT, so you wouldn't feel guilty if this happens, but so there are some exercises that say compute the centers of GLN, SLN, and so forth. Don't try to do it by hand. I mean, well, do it if you want, but the thing is, after what we did today, it's really easy to compute the centers of these algebras by just using a theorem instead of trying to compute what are the matrices that commute with all other matrices. If it is in the exercise, just think about what Engel's theorem says. The center is easy to find for upper triangular matrices, for example. All right. I'll see you, I guess, on Thursday. Yeah, well, if you have any questions, just send me an email, I guess. And I'm in my office every day. And you can speak Portuguese to me, I guess. All right, see you guys.